Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about the exponential distribution. We're going to derive the distribution from first principles, then we're going to apply it to some real-world data, and then we're going to talk about its properties. Let's get to it. We're going to use a motivating example where we want to model the time until an earthquake occurs. And that time is represented by a random variable t, which is a continuous random variable because we're modeling time, so it's natural to represent it as being a continuous quantity. We're going to make the following assumption in order to build a model, which is that the probability of an earthquake within a period of length epsilon is equal to lambda epsilon, where lambda is some constant that captures the rate at which earthquakes occur. And this probability is the same no matter what has happened before. So the idea is that we're considering earthquakes happening, and if we have waited until a certain time t, and no earthquake has arrived, now the probability that we see an earthquake between t and t plus epsilon is always going to be equal to lambda epsilon. So essentially what we're saying is that earthquakes just arrive from time to time at a certain constant rate. It's not that they're going to happen more often here than here. So when we're considering the time until the earthquake occurs, no matter what has happened before, the probability that the earthquake occurs within an interval of length epsilon is always the same. It's always lambda epsilon. This might ring a bell. When we were talking about the Poisson random variable, when we derived the Poisson random variable, we also used earthquakes as an example. And what we said is that we were considering a certain interval, maybe a year. We're interested in the probability that a certain number of earthquakes would occur within a year. And we made the same assumption. We said that earthquakes happen independently, and the probability that there's a single earthquake within an interval of length epsilon was exactly lambda epsilon, like what we're saying now. And it turns out that the assumption for the Poisson random variable is indeed the same as the assumption we're making for the exponential random variable to derive the exponential random variable, but there's a crucial difference. In the case of the Poisson random variable, we're interested in the number of earthquakes. So here I've drawn kind of like 3 earthquakes occurring, the number of earthquakes that would occur inside a certain interval. For the exponential random variable, it's different. It's the time until an earthquake occurs. So the Poisson random variable is discrete, the exponential random variable is continuous. However, the two parametric models are derived from the same assumptions. It's just that we're modeling different quantities. Okay, so more rigorously, or more mathematically rather, what are we saying about this random variable t? We're saying that if the random variable is greater than a certain constant t, then the probability that t is between that constant and that constant plus epsilon is equal to lambda epsilon when epsilon goes to 0. Okay, this is a conditional probability which captures this idea that nothing has happened until this time, and now we look at an interval of length epsilon right after that time. This is more mathematically the assumption that we're making in order to derive a probabilistic model for the time of arrival of this earthquake. Now, what we ask is, if this holds, what does the distribution of t look like? In general, when we derive the distribution of a continuous random variable, we can choose whether we want to derive the CDF or the PDF. It's often easier to derive the CDF because it has an interpretation in terms of a probability. So that's what we're going to do now. We're going to try to transform this conditional probability into an expression that depends on the CDF of t, and then we'll use that to try to derive the CDF. So this conditional probability, what is it? Just by definition, it's equal to the intersection between the probability of the intersection between this event and this event, which is here, and the probability of the event that we're conditioning on, divided by, the probability of the event that we're conditioning on. Now, if you look carefully at these two events, you will realize that this is just a subset of the event on the right, because if t is between t and t plus epsilon, in particular, it's greater than t. So the intersection is just equal to this event that t is between t and t plus epsilon. I realize that I'm using t for two things, which I think is clearer when you look at it, right? This is the random variable t, and this is the constant t, but but when I say it out loud, sometimes I suffer to try to find an alternative word, but I think you got it, right? All I'm saying is that the intersection is equal to this event. And then we, of course, divide, but we will have to divide. And now we're going to write this expression in terms of the CDF of t. So if you remember, what is the probability that a random variable is between t and t plus epsilon? It's just the CDF at t plus epsilon minus the CDF at t, divided by 1 minus the CDF at t. Maybe I should have said this at the beginning of the video, that every time we have a random variable, there's a squiggly line on top. If you don't see a squiggly line, that means this thing is just a constant that you can replace by a number. I probably should have reminded you of this before going into all of these derivations. Hopefully you remembered from other videos. Anyways, now we have managed to express our conditional probability in terms of the CDF, so we're very happy. We're going to have to do some more work though. In particular, we're going to have to take the limit where epsilon goes to 0. In order to do that, it's going to be convenient to work with the survival function instead of the CDF. This is the only time I think in the course where we're going to use the survival function, so don't worry too much about it. This is just a change of variable, but it is a function that is commonly used in statistics, which is just 1 minus the CDF. Again, don't worry too much about it. For this particular case, it's just more convenient. You can think of it as a change of variable. So we're going to change this expression, do a change of variables so that we express this fraction in terms of the survival function. So we just plug in 1 minus the CDF for each of the times the CDF appears, and we get that this expression is equal to s of t minus s of t plus epsilon divided by s of t. Great. So now what are we going to do? We have arrived at the point where we're going to take the limit when epsilon goes to 0 and set this equal to lambda epsilon. That's what we're going to do. So we take this expression and move all the parts that depend on epsilon to one side and take the limit when epsilon goes to 0, and this is what we obtain. Okay, maybe you want to pause the video and take a look, but essentially we're just moving things around here and then taking a limit when epsilon goes to 0 of the part of the expression that depends on epsilon. All right, so as a summary, our assumption about the arrival of earthquakes is exactly equivalent to this expression where minus lambda, this constant rate at which the earthquakes occur, is equal to 1 over the survival function times this limit. Let's take a closer look at this limit. It's the value of the survival function at t plus epsilon minus its value at t divided by epsilon when epsilon goes to 0. So what is this? This is just the slope of this survival function at t, or equivalently, it's the derivative of the survival function. And now if we look at this expression, which is 1 over the survival function times its derivative, this is nothing else than the derivative of the logarithm of the survival function, if you remember your calculus. So now this is great because we can just integrate on both sides. Before we do that, maybe let's realize what is going on. What we have done is we have derived a differential equation from our initial assumption in terms of conditional probabilities. This is a differential equation that involves the survival function and hence the CDF. By solving that differential equation, we're going to derive the expression of the CDF for our parametric model to represent the time until the earthquake occurs. So let's do that. We just integrate on both sides. We have that minus lambda t, we integrate with respect to t, of course, minus lambda t plus a constant is equal to the logarithm. And now we're going to just take exponentials on both sides. So this means that the survival function is equal to some constant times exponential of minus lambda t, and that is equal to 1 minus the CDF. So moving things around, what is the CDF equal to? It's 1 minus some constant times an exponential. And now we're going to impose that we start counting at 0. Okay, so we start counting at 0. The probability that an earthquake occurs before 0, we're going to assume is 0. Okay, so we're not counting, we want to know the time an earthquake occurs starting at the origin. If we do that, then f of t at 0, which is equal to 1 minus this constant, has to be equal to 0. So this implies that the constant is equal to 1, and we have arrived at this expression for the CDF, which follows directly from this assumption about the conditional probabilities. Directly, maybe not super directly, because we had to derive this differential equation and solve it, but I mean it's a direct consequence. So now if we want to find the PDF of the time until an earthquake occurs, we just take a derivative. We realize that this PDF is an exponentially decreasing function. And that's an exponential parametric model. The PDF of an exponential random variable t with parameter lambda is exactly equal to the expression we have derived. It's lambda times an exponential where we multiply lambda times t, okay, and then we take minus and then an exponential, which starts at 0. Okay, we impose that we start counting at 0 if you want. What does this function look like? It looks like that, decaying exponential. What happens if we increase this constant rate of earthquakes? Then an earthquake will happen earlier, so we expect the density to be higher here. I should have asked you to pause the video and think about it. Now it's too late. And indeed, that's what happens. You increase it even more. That's how it's always good when you're looking at a parametric distribution that depends on a single parameter or a small number of parameters to think how the density would change when you modify that parameter and if that makes sense to you. And in this case, I would argue that it makes a lot of sense. Excellent. So now let's apply this to some data. Exponential distributions are often used to model time of arrival. So the time at which a call arrives, or an email arrives, or an earthquake arrives, or a particle decays, or there's a neural spike in a neuron. For all of these cases, exponential distributions are used in practice. So here we're going to model the time between phone calls. So I have received a phone call in a bank. This is a real data set from a bank in Israel that we already used for the Poisson model. Again, both of these models model different quantities, but they have the same assumptions. So we're going to use the same data set, call center in Israel. There are calls arriving. We have the times at which the calls arrive. We're going to consider all the calls between 6 a.m. and 7 a.m. on weekdays. Notice that we don't consider the calls over the whole day, because then this assumption that the calls are kind of arriving at the same rate at any time certainly does not hold, right? Because there's going to be, for example, many more calls during the day than during the night. So that's why we restrict ourselves to a certain period of the day where we think that the rate of arrival should be approximately constant. Okay, so we're going to model that. We have a training set which have calls from January to June of 1999, test set July to December of 1999. And now we're going to compare first a non-parametric density estimate based on kernel density estimation. We have a video that explains how we compute that. And what we see is that the correspondence between the test data and the training data is reasonably good, except for very short phone calls. So it seems that we have many more short phone calls in the training data as opposed to in the test data. And then we see this noise in the estimate, which is typical of non-parametric models when you make them granular enough, because we're overfitting a little bit some noisy fluctuations in the data. Let's take a look at what an exponential model fit using maximum likelihood. We'll explain exactly how to do this in the following video. What that looks like. So here it's kind of interesting because we underestimate the number of short calls. Otherwise, the fit looks very nice and it adapts very well to the data, and it doesn't have these artifacts, these noisy fluctuations that the non-parametric estimate has. But we do underestimate the number of calls. The reason for this is that the exponential distribution does not have the flexibility to fit the number of short calls. And in fact, if you look at the kernel density estimate, the number of short calls in the training data is actually really high. So I don't know exactly why. You would have to really go into the data and realize why. But the parametric model was not able to account for that because it can only fit, the whole. It doesn't have the flexibility to fit patterns that do not correspond to its assumptions. So it actually does not overfit the number of calls in the training data to the extent where it kind of underfits them. Okay, it's not able to tell that for this particular data set, it's kind of more likely to have shorter inter-arrival times between calls, at least within those times. So hopefully that gave you a taste. We already did this in much more detail for discrete models, but you saw a little bit maybe the trade-off between the non-parametric model and the parametric model. All right, so now let's delve a little bit deeper into the properties of the exponential distribution. And in order to do that, we're going to take a little bit of a closer look to this data. In particular, we're going to be interested in how the distribution of the time between calls changes if we consider calls where the time is greater than a certain constant. Here we're going to be looking at another interval between 9 and 10 a.m. The reason is that there are more calls within that interval, so it was just easier to compute the conditional distributions that you're going to see in a moment. So what are we going to do? We're going to say, first, let's take a look at all the calls. This is what the histogram looks like. This is what the normalized KDE density estimate looks like. Okay, so this is a valid density. Now, we're only going to be interested in calls that happen at a time that is greater than 25 seconds. So we have gotten rid of all the calls that were here. Bye-bye. We only keep the data points that are above 25 seconds. And now we normalize to build the conditional density. This is the conditional density. Once you're greater than 25 seconds, this is the density of probability that we observe. Maybe you start seeing that this looks suspiciously like this, except that shifted to 25. Let's do the same thing again, but with 50. We throw away all the calls where the time is smaller than 50, and we renormalize to build the conditional density. Again, it looks very similar, but shifted. 75 seconds, we throw away all the calls below 75 seconds, renormalize. Very similar, but shifted. Why is there noise, much more noise now? Think about this, maybe pause the video. The reason is that this is a non-parametric estimate and we have many less data because we're restricting ourselves to calls above 25 seconds. And as we saw, there are more calls for smaller times. So it's natural for this to be noisy, but still the general shape looks very similar. So when we put them on top of each other, I shift them back and I put them on top of each other, we see that the conditional densities are all very, very similar, except that they start at the time where of course, they have to start at the time where we're considering. So if we consider calls above 25 seconds, it has to start at 25 seconds. But if we shift them all back to the origin, they look very, very similar. This suggests that the time that you have to wait for the next call is always the same no matter how much you have waited, at least approximately in this data. So let's see. Let's take a look at whether we can explain this in terms of the properties of the exponential distribution. We're going to look at the probability, not the probability, the CDF of an exponential random variable t when we know that t is greater than a certain constant. And then we will differentiate the CDF to find the conditional density and see if we can explain the phenomenon that we just observed. Again, we start with the CDF because it has an easy interpretation in terms of probabilities. What is this conditional PDF? It's nothing other than the probability that the random variable is smaller than a certain value t, conditioned on it being larger than a value t sub 0. What is this conditional probability? It's just the probability of the intersection, you're above t0 and below t, divided by the event that we're conditioning on, the probability of t being greater, of the random variable being greater than t0. Now we can plug this here, the CDF here. So this is the CDF at t minus the CDF at t0. Here I've made a typo, right? This should be bigger. Anyways. And then we divide by 1 minus the CDF at t0. And now we plug in the exponential CDF that we had derived, and we get this expression. But now what is this expression equal to? We take out, if we divide by e to the minus lambda t0 everywhere, we see that this is just equal to 1 minus the exponential of minus lambda at t minus t0. If we differentiate this, we quickly see that this is just an exponential distribution shifted to t0, which is exactly what we were seeing from the data. So when you take, it is an exponential starting at t0, and now we're going to see, I'm going to explain like in a moment why this is memoryless, but I want to first show you graphically what we're talking about. We're saying that if you take an exponential and now you kind of cut it, for example, at 2, and you only consider the time afterwards, and you renormalize to make it a valid PDF, boom, you get an exponential again, except that you start at 2. And now let me go back to this term. We usually say that the exponential distribution is memoryless because of the fact that if you have waited, let's say, 1 hour and the time of wait is exponential, then the time you're going to wait after that hour is actually the same as in the beginning. So this is like, I had this flight that was canceled during the COVID-19 pandemic, and then I was calling Lufthansa to try to get it reimbursed, and I had exactly this feeling. No matter how much I had waited, I would have to wait exactly the same. I would have to wait forever, it seemed. So this is, in case that gives you a little bit of an intuitive feeling for what it means to be memoryless. No matter how much you have waited, the distribution until the earthquake occurs or the phone call comes or particle decays has the exact same distribution as at the beginning. And incredibly, because this sounds a bit weird the first time you hear it, we see it exactly from the data. Okay, so let me go back to this plot because I think that it shows this beautifully. So again, this is when we start conditioning on times that are above certain values, and then we shift back the conditional densities. They're exactly on top of each other. So here, this exponential, the assumptions of the exponential distribution really hold for these phone calls. Let me go back. All right, and as I had shown you, if you want to think about this a little bit intuitively graphically, it just means that when we cut this PDF and then we renormalize, we always get back an exponential but shifted. All right, so what have we learned? We have derived the exponential distribution from first principles, and then we have learned that the exponential distribution is memoryless, and this is a property that you actually observe in real data. And that's all I got. Thank you very much.